Hi everyone, I'm Enrico Zardini. I'm a PhD candidate at the University of Trento in Information and Communication Technologies, and I'm also enrolled in the transdisciplinary program in Quantum Science and Technologies. Today, I will talk about Quantum Annealing Learning Search implementations, a paper that I published together with the students Andrea Bonomi and Thomas Temin, professors Enrico Blanzieri and Davide Pastorello, and the researcher Walter Cavecchia. But first, let me provide some additional details about the publication. The article, Quantum Annealing Learning Search Implementations, has been published in March 2022 in the journal Quantum Information and Computation. And for this work, I would like to acknowledge the QATN, the joint lab between the University of Trento, FBK, INFN, and the CNR for their support, but also the Jülich Supercomputing Center, which has provided us with the access to the D-Wave quantum annealer, on which we have run the experiments. So here is the outline of my talk. So first of all, I will give a brief introduction to some background concepts that will be useful later on. Then I will describe the structure and the main features of the Quantum Annealing Learning Search algorithms, also known as QALS. After that, I will present the implementations in C++ and Python with their respective advantages. And finally, I will describe the experimental evaluation, so the problems taken into account, the results obtained, and I will conclude with a brief summary of the main points. So let's start with the background concepts. So first of all, from the perspective of a computer scientist, quantum annealing is a heuristic search for solving optimization problems. And it is characterized by three main steps. So first of all, the problem must be expressed as QUBO, which stands for quadratic unconstrained binary optimization. And the output of this first step is a QUBO matrix Q. Then the matrix must be embedded in the annealer topology. And this requires moving to the Ising formulation, which is the one that the annealer understands, and then mapping the problem variables on the real topology of the annealer. Finally, there is the evolution of the system towards the ground state, which gives the solution by means of measurements. So, more in detail, QUBO problem is an NP-hard problem, which is defined as the minimization of a function f whose domain is the set of binary variables 0, 1 to the power of n, and whose codomain is the set of real values r. So in practice, a QUBO problem is defined in terms of binary variables xi and xj, and real value coefficients qii and qij, which can be arranged in an upper triangular matrix. And actually, there is also a more compact representation of a QUBO problem, which is the one shown at the bottom, which is defined in terms of binary vectors x. So, as I just said, the annealer is not able to process problems expressed as a QUBO. So, first of all, we need to move to the Ising formulation. Indeed, the energy of the Ising model, which is provided in equation 1, describes also the spectrum of eigenvalues of the Hamiltonian of a quantum spin glass, which is a network of qubits. And so, in order to move from the QUBO formulation to the Ising formulation, we need to perform a linear transformation from the domain 0, 1 to the domain -1 + 1. So if we look at the equation 1, we can see that there are these binary variables, z, I, z, j, defined in the spin domain, -1 + 1, and some real coefficients, theta I and theta ij, that can be arranged in a matrix called the weight matrix, and it's theta. The main difference with respect to the QUBO matrix Q is the presence of 0 values in correspondence with the pairs ij for which there is no edge inside the spin graph. So here we have also the concept of graph and related nodes and edges. However, the topology of the quantum annealers are typically not complete. For instance, the Pegasus topology provided by D-Wave has roughly 5,700 qubits with a connectivity of 15. Hence, an embedding step, which is a mapping step, is required. And this typically leads to the formation, to the building of some qubits chains. The wave provides some tools, such as the embedding composite class, to perform this step in an automatic way. However, the maximum embeddable problem size for a complete QUBO matrix Q is around 170 binary variables, so not too much. And after the embedding, there is the annealing step, which drives the system into the ground state. And if the problem encoding is correct, the ground state corresponds to the spin configuration that encodes the solution to the problem of interest. And the solution is retrieved by means of measurements. The process is then repeated multiple times to increase the probability of reaching the real ground state. Indeed, the quantum annealers are machines that are subjected to noise and temperature effects, and so there is not 100% probability of reaching the ground state. Then let's move to the description of the algorithm of QALS. Well, QALS is a guided meta heuristic proposed by Pastorelli and Blanzieri in 2018 to solve optimization problems that are not cannot directly embedded in the annealer topology. The main features of QALS are the usage of a taboo matrix to penalize already visited solutions, then the usage of random permutations and a direct mapping on the topology graph, and finally an iterative structure which is inspired to simulated annealing. So, more in detail, given a set of solutions Zj to penalize, and it is worth highlighting that these solutions are defined in the spin domain, -1 + 1 to the power of n. The taboo matrix S prime is defined as shown in the equation in the middle of the slide. So basically we have an outer product, the identity matrix of order n, and the diag of Zj, which is just a matrix of order n that contains on the main diagonal the vector Zj. And by summing the matrix S prime to the QUBO matrix Q prime, defined on the same domain, -+1 to the power of n, we are able to introduce energetic penalties on the variables Zj. Then let's consider the problem encoding that is exploited by QALS. Well, basically, the encoding of the QUBO matrix Q prime into the annealer is given by the equation shown here. So here we have a permutation matrix P of order n and its transpose Pt, the QUBO matrix Q prime defined on the spin domain, a scaling factor lambda, which is decreased throughout the iterations, the taboo matrix S prime defined again in domain -1 + 1, and the adjacency matrix of the annealer topology A. The big dot represents the Hadamard product. So in practice, the taboo matrix S prime is rescaled and summed to the QUBO matrix Q prime that represents the problem. Then a random permutation is applied to the resulting matrix, which is, after that, there is a direct mapping on the adjacency matrix of the annealer by means of an Hadamard product. And thanks to S prime, the algorithm, after some iterations, does not search anymore just for solutions of subproblems, but for solutions of the entire problem. Indeed, the taboo matrix S prime is initialized to 0 and then is populated throughout the iterations. So let's look finally at the iterative scheme. Well, basically, at each iteration, new candidate solutions are generated through quantum annealing. And since we are applying a permutation before calling the annealer, our remapping is then needed to obtain the solution in the original solution space. And instead, the rejected solutions are used to update the taboo matrix S prime, which is initialized to 0. However, also suboptimal acceptance, so acceptance of non-optimal solutions, is allowed according to a certain probability, which is decreased throughout iterations according to a temperature parameter P, which is inspired to simulated annealing. And this parameter P actually controls also the degree of perturbation of the permutation matrices P, Pt, and also of the solutions. Indeed, there is a certain probability of perturbing the solution returned by the annealer before accepting or discarding it. And actually, so in practice, at each iteration, the permutation matrix P is perturbed in a different way, in a different random way. And the algorithm terminates either due to convergence, there are some parameters that can be tuned in order to reach convergence, or by reaching the maximum number of iterations. So now let's move to the implementations. So in this work, two implementations in different programming languages are introduced, and the languages are C++ and Python. The advantage of C++ is a higher efficiency in the classical part of the algorithm, whereas the advantage of Python is the presence of native APIs to interact with the quantum annealer provided by the wave. And actually, there are two main differences with respect to the original formulation of the algorithm. Indeed, first of all, the QUBO problem and the taboo matrix, Q and S respectively, are defined on the binary domain 0, 1 to the power of n, instead of the spin domain -1 to +1 to the power of n. Hence, also in terms of notation, I will use Q and S instead of Q prime and S prime. At the beginning, we performed some initial experiments using the spin domain, but the results were almost the same, and hence, in the end, we decided to just stick to the binary original, the domain in which the QUBO problems are formulated, so the binary domain. And the other main difference is the management of permutations, so how the permutation matrices P and PT are managed inside the actual implementation. So in practice, we noticed that the computation of the matrix product PT Q plus lambda SP was really slow. And so we decided to change the representation from a permutation matrix P to a permutation vector perm. For instance, let's just look at the example in the bottom of the slide. So here we have a permutation matrix P and the corresponding permutation vector perm. The value 3 in the first index of the vector perm means that the value 1 is located in the column with index 3 inside the first row of the matrix P. And this change of representation has some advantages. First of all, the complexity for perturbing the permutation is reduced from quadratic complexity, a big O of squared n, to a linear complexity, big O of n. Indeed, the number of elements that must be shuffled and perturbed is not anymore squared n, but it's just n, it's a vector. And the other advantage is the possibility of retrieving the elements that will be mapped into the annealer topology, A, without having to compute the entire permuted matrix PTQP. So let's just look at the example here. So we have a matrix Q, a permutation matrix P, the corresponding permutation vector perm, and the permuted matrix PTQP. For instance, if we want to know the element that is located in the cell with row index 1 and column index 2, which is 20, we have just to look for the index of the values 1, 2 inside the perm vector. And the indices of 1 and 2 are 3 and 4 respectively. And hence, we have just to look for the content of the cell with index 3, 4, which is exactly 20. But it is also possible to improve this procedure. Indeed, we can compute the inverse of the perm vector by running a procedure with linear complexity once at the beginning and reuse the inverse vector multiple times. In this way, the complexity of the problem encoding operation, without considering the perturbation of the vector, becomes linear from quadratic. Indeed, the annealer topology, for instance, the Pegasus topology has a connectivity 15, and so given a matrix of order n, we have just to search for 15 times n values. And the search, the reading of a value from an array has a constant complexity, so the overall complexity is linear, is a big O of n. And also the inverse vector can be used to map back the solution returned by the quantum annealer to the original solution space. Indeed, we need to perform this remapping step, as I said previously. And then let us consider the C++ implementation first. Well, actually, the main issue we encountered is the lack of C++ APIs to interact with the quantum annealer by the wave. And there are actually two possible solutions we have taken into account. The first one consists in embedding a Python function in the C++ program. The second one instead consists in interacting with the child Python process. And we choose the second one because actually we run all the experiments on the cloud interface provided by D-Wave, that is lib. And in lib, there is not the python.h header file, which is needed to embed a Python function in C++. So we decided to interact with a child Python process. And this Python process is created at the startup of the program through a fork operation. And it has two main tasks. First of all, to provide the parent process with the topology of the QPU, so the active nodes and edges. And then to submit the problems to the solver and to return the solutions to the parent process. The communication is performed by means through an anonymous pipe using a simple message protocol we devised. And the overhead of this message exchange protocol is around 1 second for one call to the annealer. This might seem not so much, but it might cancel the benefit of using C++ instead of Python. And the other important topic to discuss is related to random operations. Indeed, the QALS requires lots of random operations, and mainly in terms of permutations. And the algorithm we chose to perturb the parent vector is the Fisher-Yates algorithm, which produces unbiased permutations. Actually, this algorithm requires a random number generator, and we chose the Mersenne twister. Indeed, this random number generator has a quite high period, the value shown here, and the period is basically represents the size of the internal state. And actually, this value is not enough to cover the entire permutation space of a vector with 5,000 elements. But this is the best trade-off we found between efficiency and coverage of the permutation space. Actually, we considered also other possible random number generators. First of all, the rand function provided by C++. But actually, it does not yield numbers with uniform probability due to the usage of the modulo operation to restrict the random value to the desired range. Moreover, the period is quite small. Indeed, it is typically 2 to the power of 32. Another possibility we took into account is to use the quantum annealer as a random number generator. Indeed, the numbers generated by a quantum process can be considered truly random. And so it is an interesting approach, and the protocol is quite simple. The first step consists in providing the annealer with a QUBO matrix, such that each qubit has the same probability to collapse to either 0 or 1. For instance, to this end, we can provide a null matrix, a QUBO matrix with all the 0 entries. At this point, we can, after the annealing process, we obtain a binary string, which can be split 0 or more times to obtain 1 or more integer values. And actually, this process is really interesting, but unfortunately, it's quite expensive. Indeed, the overhead would have been too much due to the high number of calls from the QALS algorithm, but also the high number of variables that are taken into account, roughly 5,000. And so we decided to use the Mersenne twister. Instead, regarding the Python implementation, there are not specific details to mention, so I will just briefly describe the embedding procedure, which is the same used by the C++ implementation. So it's quite simple. The first step consists in retrieving the list of working nodes and working edges in the annealer topology. After that, we have to select the first n nodes in the list and the related working edges. And finally, we have just to incrementally map each selected node to an index of the matrix to embed. Finally, let's move to the experimental evaluation. So, for the experimental evaluation, we took into account two problems: number partitioning and the traveling salesman. The number partitioning is a problem that can be naturally represented as a QUBO problem, whereas the traveling salesman problem includes some constraints, and the QUBO problems are by definition constrained, and hence an additional step of encoding the constraints as penalties is required. And in terms of the system, we used the wave advantage 1.1, which is characterized by the Pegasus topology, with the default annealing time schedule.